Okay, so now that we've introduced the idea of concavity, let's talk about something called an inflection point. So an inflection point is a point that's on the graph of a function f where the second derivative of f changes sign, which means that the concavity is going to change sign, meaning it's going to change from up to down or from down to up, which would be when f double prime changes from positive to negative or from negative back to positive. So note that this has to be a point where the function f of x is defined, okay? So there's actually going to be a point on the graph. It's not going to be like a discontinuity or a hole or something like that. Let's draw a couple pictures of inflection points. So let's say we have an inflection point right here. The graph that I've drawn so far is concave up. You can kind of see this upwards concavity here. Then now, if this is an inflection point, then after this, I'm still going to continue on, and I'm going to make this smooth and differentiable, okay? So it's going to continue in the same direction with a defined tangent slope, but it's going to change concavity, so now it's going to come down like that. Okay, so downwards like this. So that would be, right there is an example of an inflection point. Okay, if you have a graph that looks sort of like this, right, then you can see it's concave up over here, and then at some point it changes to concave down over here. So there's some specific point which can be kind of hard to see, but there is a point in here where it's going to change concavity, and that is the inflection point. We're going to learn how to calculate the exact location of that inflection point. This can happen, where you have a defined tangent line. It can have a tangent slope, some positive, negative value, a 0, maybe it's a slope 0. It can also happen at a point where the first derivative is undefined. We draw an example of that. Here's an example where you change from downwards concavity to suddenly upwards concavity at a point right here. And I know it kind of looks like the graph goes vertical right here, but technically it's never vertical, right? It just gets really close to vertical and in fact approaches vertical. So this would be a point where the tangent line is vertical. Okay, which means that the first derivative is undefined. And if the first derivative is undefined, then it actually means that the second derivative is also undefined, technically. But that can still happen at a point on the graph where f is defined. So remember back here I said note the function f must be defined, because we must be talking about an actual point on the graph, not some discontinuity or hole. That doesn't necessarily mean that f prime and subsequently f double prime might not be undefined. They could be undefined, okay? So in order for us to find inflection points, we're going to have to do something very similar to looking for critical numbers. We're going to look for places where the second derivative is either 0 or undefined. I just want to show you one more example of like an undefined second derivative, which would still be an inflection point. Let's say you have like a piecewise defined function where on one side it's defined with some downward sloping, or some downwards curving, like negative concavity. And then on the other side, whatever new function you have has some upwards concavity, like this. But they meet at a point which ends up being basically a corner, like a cusp type of thing. That would be a point where the first derivative and also the second derivative are both undefined, but yet it still can be like a defined point on the graph. So that would also be an inflection point. All right, so let's sum up what we've said here. F double prime can change sign when one of two things happens: when its second derivative equals 0, f double prime equals 0, or when f double prime is undefined. These numbers are not necessarily inflection points, but they are potential inflection points, right? Just like how the critical numbers are potential local maximums or minimums. Okay, inflection points are basically analogous to local extremes, but one step up the derivative ladder. So, you take one more derivative and then analyze that next derivative, f double prime, and then what you're looking for, you do like the exact same process as finding local extremes, except what you're really finding are inflection points. And it's not the exact same process because You don't talk about mins and maxes, and you don't distinguish between changing from up to down or changing from down to up. Like, you don't really distinguish types of inflection points, but otherwise it's very, very similar. Now, for the first derivative, when we found all these numbers that were where it was 0 or undefined, we called those critical numbers. And unfortunately, there's no official, like, vocab term for the zeros and points where the second derivative is undefined. Like, these don't have a name. We don't call these critical numbers or anything like that. So I met a mathematician named Roger Hergert, and Roger Hergert said these should have a name. And so he gave me his business card, and he was trying to popularize the use of this term. He wanted to name these numbers after himself. So I just think that's delightful. So I sometimes refer to these numbers as Hergert numbers, as per his request.